Gold foil experiment. Rutherford shot a radioactive particle at the gold foil. So first thing you got to figure out, what did he shoot at the gold foil? And then, so that's kind of like the first thing here. I don't want to number it 1, but that's the first thing. And then, what did he prove? So what was proven about the atom? And there's 4 things. 1, 2, 3, 4. And we'll fill in those 4 after the video, okay? So if you can't keep up and write your notes at the same time, at least just watch, pay attention. So yeah, 4 things that he proved about the atom. But this is important. What did he shoot at it? And then we will go over it. So it's only 47 seconds.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
It's actually not the
the
best video, but it does cover, and she doesn't specifically say this was proven. So you kind of have to, I'll play it one more time, you kind of have to pick out what she says. We've gone over it already, basically. So let me just play it one more time. But again, there's really, I'm kind of stretching 4. 2 of them are kind of, two are combined to 1, sort of, but I separated here. So really there's 3 things, but I separated it in 4. So again, what did he shoot? And then what were the 4 things proven? I don't think she actually mentions one of them. You should already know.
In 10, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Okay, so they're about to fade out more. So most of them went straight through because that proves the atom is mostly this. We already talked about it. The ones that make a direct hit will bounce straight back. But some of these alpha particles, if they just like this one, if it gets close to the nucleus, it might actually be deflected. That's what she kept saying at different angles. So if you were to look at that screen, most go straight through and hit here, but some are bent. So they're deflected, and then sometimes you saw them shooting back. So again, this is not, it's a good video for visual, but she doesn't go through all the details very well. All right, let's talk about it. What are the 4 things that, first thing is, that we've said over and over again, we said it today, atom is mostly empty space. Atom is mostly empty space. Not our atom, but most atoms. Our atom's smarter. Adam Stanley, I think he's funny, but he might have some screws loose. Number 2, what else? Small, dense nucleus. Very good. So before this experiment, they did not realize the atom had a nucleus. They thought it was like the plum pudding model, right? Just kind of this like gel type substance, like the whole thing. So when she said that, let me get to the picture here. That's better. That this is the low mass electron, that most of the atom is that fuzzy stuff there. That remember, this isn't actually how it looks. This is just kind of how we visualize it. There isn't actually this spherical shape. It's kind of, the shape changes a little bit depending on the number of electrons. It gets real confusing. But this is fine. If you visualize an atom looking like this, you're good to go. So the low mass electron, let me quick show you what she means by that. So if we go here, the electron has a mass of 0. So it actually has a mass. It does have a mass, but it's so small we say 0. Remember, the mass is on top. What's the bottom number called?
Charge.
Charge, right. So the mass is 0 for an electron. So therefore, mostly empty space. But which two particles are in the nucleus? Protons, neutrons. I hope other people with me besides Colin here. Proton mass has a mass of 1. Neutron has a mass of 1. So those two are in the nucleus, so that's why it's dense. You have these little tiny hard particles, protons and neutrons, packed inside that nucleus. So if you hit it, it's going to be like hitting a wall. Okay, that's why those particles bounce back. What particles? What did they shoot? What did he shoot?
Hydrogen, alpha particles.
Alpha, right. So we shot alpha particles, and if you look at alpha particles right here, it's positively charged. That's a +2. I know there isn't a plus sign there, but it's positive. So alpha is 4/2 He. All right, I'll squeeze that in here, 4/2 He. So alpha particles are positive, so when they hit that dense nucleus, they bounce back. Now, the next thing that I was starting to talk about there, where am I? Back to this. So these particles that kind of pass through but get close deflect. That's because alpha is positive and nucleus is positive. Nucleus is positive. And that's because the protons, put in parentheses, there's protons in the nucleus. I feel like I'm going very slow through this, but I'm doing it on purpose because this is real important to remember. Okay, not just about this experiment, but because all this is true. This is true now. The most current model. Most empty space, dense nucleus, positive. So it's all stuff you need to know. Last thing has to do with number. You can kind of put 4 and 2 together. All right, go ahead. You can. It's like Jeopardy. You're going through the whole. You're doing the whole category. Oh, that's this one. That's not wrong, but that's this. So we're good. That's okay. Good try. Has to do with this. Small dense nucleus. All atoms have a mass. Where is the mass located? In the nucleus. All mass located in the nucleus. That's really important to remember because that helps you understand the math when you subtract those numbers like Colin was doing with the warm-up. The reason you can do that, you can subtract the protons from the mass to get the neutrons is because, look up here, this. Protons have a mass, neutrons have a mass. Electrons do not. So if we're dealing with carbon with a mass of 12, it has 6 of these and 6 of those. 6 plus 6 equals 12. The electrons have nothing to do with the mass. Therefore, since electrons are outside the nucleus, protons, neutrons in the nucleus, all the mass is located in the nucleus. So, here's a good word for you. It would behoove you to memorize all of this. Except, you know, I'm not a fan of just memorizing. I want you to learn and understand as well. So yeah, I need you to know this and remember it, memorize, but also be able to explain it to me, right? So mass is in the nucleus. Nucleus is positive. Small, dense nucleus. That's why I say 4 and 2 are kind of the same. Because without that, this doesn't make sense. And then atom is mostly empty space. And alpha was shot, okay? So that all kind of covers a lot of important information. Questions on the gold foil? Okay. All right. So I'm done with this for a little bit here. Lights, please. All right. So we talked about cathode ray. We talked about gold foil. We went through all the models of the atom. What's the most current model called? Wave mechanical or quantum mechanical, right? And what's the other common term for it? Not wave mechanical, not quantum mechanical. What's the other term we could use? Yeah, the cloud, the electron cloud model. Right. All right. So, real quick here, let's make sure we understand. You know what? I want that light to work. Who wants to take a walk? No one wants to take a walk. Morgan, thanks for volunteering. Walk back to the door, please. It'd be good for you. Stretch your legs, wake up a little bit. Act as if you're going in the back room. Thanks. Appreciate it. All right. So, what?
How does that work?
Because the sensor, if you turn around, there's like a thing on the ceiling in the back there. It's a light sensor, but that row, the sensor's in the back of the room. So if you're up here moving around, it's not going to work. Yeah. Okay. All right. So we talked about cathode ray. We talked about the gold foil. All right, we're in a good spot here. All right, let's do this. An electron has a mass. This is kind of random, but it's just part of what we're learning about. So we learned about cathode ray, the gold foil, the nucleus, the atom itself, mostly empty space. But an electron has a mass of 1/1840 of a proton. Now the reason I tell students this, it's such a technicality, like who cares, why do we need to know this? Unfortunately, I've seen it on the Regents a few times. It says, what is the mass of an electron? That's your answer. 1/1840 of a proton. What does that mean? You need 1,840 electrons to equal the mass of a proton, right? So if we had kind of like a scale here, okay? If we had one proton over here, that would be equal to 1840 electrons to be balanced. That's what that means. Okay, so you need a lot of electrons. So basically, when we say electron is 0/-1e, it's technically not 0, but that's really small. Because protons are really, really small. Electrons are even smaller, right? So I just want to throw that out there just because of that foolish question. I don't think you learning this helps you understand chemistry more, but I got to teach it because, or at least tell you just in case. All right, so that little question could be on there. Hopefully not, but that's the only reason I talk about that. All right. Now, if you go to your reference tables, please, go to your periodic table. Go to your periodic table. All right. I got a couple things we're going to be talking about here. Now, I need to get a rope in here. You guys ever play tug of war? Yeah, we're going to be playing either on Wednesday or Thursday. So we'll split you guys up, and you're going to be playing that in here. So bring your trippy shoes and your gloves. All right. Why would I be playing tug of war with you guys? Ooh, forces. Mike's on his A game today. Good thing. Just a little bit there. Sort of. If you look at your periodic table, if you go to the group 1, look at hydrogen. What's its electron configuration? 1. Let's write this down in our notes. So hydrogen has an electron configuration of 1. What's underneath H? Li. What's the configuration? 2-1. Sodium. 2-8-1. We'll just do one more. Potassium.
2-8-1.
Okay. Do you guys remember what I've talked about so far with what those numbers represent? Levels, energy levels. Good. Electron levels. Give me another word. Starts with an S. Eggs. Eggs. Starts with an S.
Shell.
Shell. Thanks, Adam. Word association. Okay. These are called electron shells. All right? So the atom of hydrogen kind of looks like this. Lithium looks like that. Sodium looks like that. And potassium looks like that. So what do you notice about the size of the atom as we go down group 1? It increases. Why does that make sense? Because potassium has 4 energy levels, or 4 shells, or 4 layers. Layers is kind of a bad word. I use the analogy of onions. Imagine these drawings are onions. So you have more layers to peel away before you get to the center. That helps you understand the concept, but that's not really exactly how it works. But I think you can see it, that as we move down, the number of electrons goes up and the number of shells goes up. Who remembers what model this is? Not the plum pudding. Bohr, very good. So the Bohr model is useful for teaching this. What am I teaching? Atomic radius. Now, atomic radius essentially is the distance, this is not the definition, it's just how I teach it, it's the distance from the center of the nucleus to the last energy level. So the radius of these atoms will increase as we move down the group. I'm not going to give you that definition yet. Okay, we'll get into that probably Wednesday. But there's this other thing called ionic radius. So what is an ionic radius? Well, first you have to understand what an ion is. So I just briefly explained atomic radius. Briefly explain that. That has to do with how many electrons there are. So as you move down the group, if you guys look at any group, let me get out of my thing here. If you look at any group, okay, look over here. We start out with 1 proton, 1 electron. We get down to 87 protons, 87 electrons. 4 and 4, 88 and 88. Go over here to group 15. Start with 7 electrons, go down to 83. Start with 2, 86. So it makes sense, look back up here, that as you move down groups, you're going to have more and more energy levels because you have more and more electrons. Does that make sense? So this is larger than that. Like a little, imagine, I don't know, what do they call those little onions? Like medallions or something? You ever seen a real little onion? Mm-hmm. Okay, well imagine a real little onion and a big fat onion. Okay, that's as you move down, onions get bigger and bigger. More layers, okay? So that's the concept. I think you get it. I hope you get it. I'll teach you more as far as the specific definitions down the road. Now, ionic radius has to do with, and there's a method to my madness. I had you write this for a reason besides the visual. We have to learn what an ion is. So let's define what an ion is. Anybody know? You learned it at some point in your travels. A charged particle. Yeah, I'm going to change that a little bit. An atom with a charge. An atom with a charge. There's 2 types of ions. There's a cation ion and then an anion. Anybody know the difference? Yes, one's positive, one's negative. I'll give you a hint. The one that's positive has a plus sign right in the word. Cation. Cation has the plus right in it, so cations are positive ions. Anions are negative. Does anyone know what the prefix AN means? Think anti. It's kind of like opposite, negative. I got nothing for this one except the plus sign. And then I've had kids in the past tell me, oh, having a cat is positive. We'll agree to disagree on that one. But I'm more of a dog person. But anyways, positive, cation, negative, anion. What does that have to do with this right here? And what does it have to do with radius? Here's the deal. How does an atom become positively charged? Remember I told you all the atoms up there are neutral. No charge. How does an atom become positive? How does an atom become negative? Very good. Cations have lost electrons. I'm just going to put E minus. They lost electrons. Anions have gained electrons. Wait a second. Who's it going to be? Who is it going to be? Who have I not talked to yet? Trevor. How losing something makes me positive? How is that possible? How if you lose an electron, you become positive?
Because it loses the thing it's bouncing out of negative.
Well, what's the charge of an electron?
Negative.
Negative. So if you get rid of something negative, you become positive. It's a life lesson. If you get rid of negative things in your life, you will become more positive. If you gain negative things in life, you will become negative. You hang around negative people, you're going to be negative. Okay? You get rid of those negative people, you're going to be more positive. Make sense? See, there's more of this class than just chemistry. All right, so now, let's figure this out. Let's figure this out. Let's talk about one of these over here. Now, let's say we have sodium. Write this down. Na, 23/11. Hopefully I can squeeze in one example of each, and then you can use this to do the worksheet tomorrow. So Na, 23/11. Who can tell me how many protons, neutrons, and electrons it has? Ariel, go ahead. Let's add this one out quick. 11 protons. 11 electrons. 12 neutrons. Very good. 23 minus 11 equals 12. This number tells me protons and electrons. Now, go to your periodic table. Look inside the box for Na. Look in the top right corner. What charge do you see, Tyler? Na plus 1. Everybody write this down. Plus 1, 23 over 11. Protons, neutrons, electrons. Oh, and underneath here, let's write the electron configuration. 2, 8, 1. Now, sodium can only form one ion, Na plus. It's a cation, positive cation. That's start to remember that. Who can tell me the protons, neutrons, electrons for this one? I'll give you a hint. It's not the same as this one. Hannah.
11 for protons, 12, and 12. No, 9.
10 electrons. Very good. Circle that number, please. What's the electron configuration then? It's not 2, 8, 1 anymore. Just 2, 8. Sodium lost 1 electron. Now it's positive. Remember, you get rid of a negative, you become more positive. So it lost 1 electron, so it only has 10. Notice how the electron configuration changes. Last thing, bell's gonna ring. What happened to the radius of sodium? If it loses that 1 electron, how many levels does it have? 2. It just lost this whole level. So it gets smaller. All right, that's all I got. Tomorrow, I will give you a worksheet practicing this stuff. I might still record myself for 5-10 minutes just reviewing a little bit more. We'll see if I have time. Have a wonderful day.